Welcome. Today, we're going to be discussing how can we use the zeros and the leading coefficient test to properly graph polynomials. So let's get started. Under example 1, it states, without the help of a graphing calculator, let's try to sketch the function x cubed minus x squared minus 2x. Now let's try to identify the turning points, and we will discuss what they are in a second. So what we want to do is we want to just sketch this function without using our graphing calculator. So what's the procedure to do that? Well, first, we got to find the zeros, or in other words, the roots. So how do we do that? Well, let's take a look at the function. And let's just try to solve for x. So in this case, let's set equal to 0. And now in this case, notice that the right-hand side, I can factor out an x for every single one of them. So now I have that x is equal to 0, and also x squared minus x minus 2 equals to 0. So we continue factoring out the right-hand side. We can see that x squared minus x minus 2, that's equivalent to just x minus 2 times x plus 1 equals 0. And now we have that x minus 2 equals 0, and also x plus 1 equals 0. So therefore, I have all my solutions. I have that x equals 0, x equals 2, and x equals negative 1. That's always going to be the first step whenever we want to just sketch our polynomial. So let me actually just do them in red, and let me actually plug them here. So my first one is that x equals 0. So here is going to have our first root at 0, comma 0. My second root is going to be at x equals 2. So let me plug that in. So that's exactly right here. X equals 2, and x equals minus 1. So if we sketch negative 1, that's about right here. So this is going to be our first step. Just find the solutions and plot them in. Now, our second step is going to use the leading coefficient test to define the end behaviors. And what is the leading coefficient test? Well, remember from our previous lesson. So if this is how my initial expression it's been defined, I'm just going to take a look at the leading coefficient, or at least the leading term, x to the third. But notice that x to the third, the exponent in the leading term, it's of an odd degree. So we have an odd exponent. And remember that whenever it's an odd exponent, I know that the end behaviors go in a different direction. Now, what's the direction that they go? Well, it's dependable all in what's in front. Notice that the leading term has a coefficient of 1. Notice it has a positive coefficient. So therefore, my end behavior is going to be defined as going down on the left and going up on the right. And this is all we need, because we know that my function needs to pass through the x-axis at these 3 points, negative 1, 0, and positive 2. And now due to the leading coefficient test, I can see that my end behavior has been defined this way, down on the left and up on the right. And that's how I'm going to be graphing my function now. So I'm just, and again, this is a sketch. This is not an exact interpretation. So I'm just going to say, well, it's going to go down on the left and it's going to go up. And it's going to hit my x-axis at negative 1, because I know that's one of the solutions. It's going to go beyond that, and then it is going to have to come down. Why does it have to come down? Because I know that at the end, my end behavior on the right-hand side should be going up. So therefore, my function needs to come down, and it needs to go one more time up in order for my graph to pass through those 2 points and end up having an n direction on the right hand side going up. So now it's going to come down and it's going to go up. And now this is a good sketch of the polynomial x cubed minus x squared minus 2x. It fits the definition, or it fits the description that was given to us by the leading coefficient test, and that is that my n behavior is going down on the left and up on the right. And also my function passes through the zeros, or the roots, which were defined as -1, 0, and +2. But before we explore this idea a little bit further, we do have to discuss the idea of multiplicity of a root, or the multiplicity of a solution. Now, looking at example 1, we can say that the solutions, or the roots, of x equals 1 has a multiplicity of 1, x equals 2. It also has a multiplicity of 1, and x equals -1. It also has a multiplicity of 1. But what do I mean by multiplicity? It's how many times it appears as a solution. Notice that x minus x equals 0, it's only appearing 1, so it has a multiplicity of 1. Multiplicity is just meaning how many times does it appear on the solution set. X equals 2, it only appears 1, so it has a multiplicity of 1. X equals -1, only appears 1, so therefore it has a multiplicity of 1. And why is the multiplicity so important? Because we do have rules for how your function is going to interact on the x-axis due to the multiplicity of your solution. If your multiplicity is of an odd number, which in this case they were, 1 is definitely an odd number, then it's going to cross the x-axis. What is crossing the x-axis? Well, the actual function itself. Because notice that here, since -1 had a multiplicity of 1, notice that it crossed the x-axis. 0 had a multiplicity of 1, so notice that it crossed the x-axis. 2 had a multiplicity of 1, so notice that it crosses the x-axis. Now, if my multiplicity would have been of an even number, and we're going to take a look at example in a second, it will only touch the x-axis. It definitely does not cross it. And I shouldn't call it it. It just does not cross the x-axis. Let's just give a small illustration of this. Let's assume that we do have a function where x equals 2 has a multiplicity of 2. So the way that we can assume, since I know that my multiplicity is of an even degree, let's assume that this is 2. If I were to be graphing my polynomial will only interact at the value of x equals 2, but it's not going to cross it just like we did on our previous example. What it's going to do is it's just going to touch it and it's going to come back down. We can have that situation, or we could also have the situation where perhaps it was already above the x-axis. So perhaps we could also have the situation where the graph would come here and at -2, it will not cross it, but it would just bounce back. And this is, notice how my multiplicity has a different interaction on the x-axis. At these 3 values, the multiplicity was odd, so that's why we were able to cross the x-axis at those values. But if you end up with a multiplicity of an even degree, 2, 4, 6, 8, 10, at that value, it's just going to touch it, it's not going to cross it, but it's just going to go bounce back. Now let's take a look at one example for that. Let's find a polynomial function with 3 zeros. So notice that here, the zeros are already given to us. -1, 3, and 3. So let's just write that out. We said we have zeros at x equals -1, -1/2, and also at x equals 3. But now notice that x equals 3 appears 2 times, so therefore x equals -1 is going to have a multiplicity of 1, and x equals 3 has a multiplicity of 2. Because notice that 3 appears 2 times on my solution set. So let's just plug that in. Let's just plot that in. So I know that I have a solution at -1/2, which is about right here. And also have one at +3, which is about there. So all I know is that those are my roots, and I just place them. Now, if I want to graph this, I need to know the end behaviors. And how are we going to identify the end behaviors? Well, we need to define our function. But since I know that those are my solutions, then I know that my function is going to be defined as x minus -1/2 and x minus 3 and x minus 3. Because remember that the factor, it's always of the form x minus the root. So now let's just rewrite this. So we got f of x equals x plus 1/2 times x minus 3 times x minus 3. And let's just expand this. If we're able to expand this expression, and we just take a look at the leading term, then we can use the leading coefficient test to define the end behaviors. So I'm going to start by just distributing this x to both of them. So now I'm going to have f of x equals x plus 1/2. So now my first distribution is x squared minus 3x. Distribute one more time, 3x, distribute one more time. So that's 9. So now I'm going to have f of x equals x plus 1/2, x minus 6x plus 9. And we're almost there. So now we still want to see the whole expanded expression. So what we want to do is now we want to distribute this x. So now if I distribute this x, I'm going to have x squared. Just realize that this is an x squared here. So x squared and x squared, because definitely x times x is x squared. So now this is actually x cubed. Distribute one more time, minus 6x. Distribute one more time, well, I'm sorry, 6x squared plus 9x. And just for formality, let's distribute the 1/2. So we're going to distribute the 1/2. So I'm going to have 1/2 x squared, and that's minus 3x, and that's plus 9/2. But for the purpose of this problem, we don't really need to worry too much about the simplification over here. Because if we want to just look at the leading coefficient, if we want to use the leading coefficient, then all we care is about the leading term. So the leading term is of x cubed. Now notice that in the x cubed, the exponent, which in this case, the exponent is 3, the exponent, it's odd. So therefore, my end behaviors are going to go in a different direction. Now, what's the direction that they go? Well, notice that the leading coefficient it's positive. In this case, it is +1. So since the leading coefficient, it is positive, and my exponent, it's odd, then I have the same situation. I have that on the left, it goes down, and on the right, it goes up. And now we have all the information that is needed for us to properly sketch this function. Because I know that my roots are -1/2 and +3, and now I know the behavior of the end behaviors. On the left-hand side, it's going to go down, and on the right-hand side, it's going to go up. So let's just plot that in there. So on the left, I know that it's going to be facing down, and it needs to go all the way to my root. And now I'm going to stop there, because now at -1/2, notice that my multiplicity was of 1. Since my multiplicity, it's odd, then we're allowed to cross the axis. So let's cross the axis. So we're allowed to cross it. Then it's going to come down. And now at the value of 3, we got to stop there, because now we got to check the multiplicity. The multiplicity of 3 was a multiplicity of 2. So we have an even multiplicity, and we're only going to touch the axis and we're not going to cross it. So it is not going to be okay for us to just cross the axis, but it's just going to touch the value and it's going to bounce back up. And now we have it. This is a very nice sketch for a function whose roots are negative 1/2, 3, and 3. And all we did was first identify the multiplicity of those solutions, plot them in there, expand the expression until we see the leading term, and then use the leading coefficient test to properly define the end behaviors. And with this, it concludes our lesson for zeros in graphing of a polynomial using the leading coefficient test.